Okay, so in this lesson we're going to learn a shortcut for evaluating the definite integral. Let's recall that we've used a left, right, and midpoint rectangular approximation method. We've also have used the definition to get the exact value as well as the TI-83. And most recently we've been focusing on using geometry formulas to find the exact value of the definite integral. Okay, so the bottom line is, in this lesson, we're going to go back to taking the antiderivative, just like we used to, increasing the power by 1, dividing by the new power, or by doing u substitution, creating the integrand into something we know the antiderivative of. You know, like 1 over u du is the ln of the absolute value of u, cosine u du is sine u plus c, and etc. Okay, so what we're going to do is, if we have the definite integral from 0 to 1 of x squared plus x plus 1 dx, what we're going to do is focus on this right here. Ignore these limits for right now. And if we were to take the antiderivative of x squared plus x plus 1 dx, we know that individually this is x to the nth power. So it would increase the power by 1 and divide by the new power. And now we're not going to put a plus c anymore because we have limits of integration. So we're going to evaluate this antiderivative from 0 to 1. So again, you take the antiderivative just like you used to, but we're not going to add a c. And you'll learn why in a few days or in a few moments. That once we take the antiderivative, we're just going to evaluate it at 0 and 1. So we're going to put 1 in first and get 1/3 plus 1/2 plus 1 minus putting 0 into all of that is just that. And then I'll just add 1/3, 1/2 plus 1, get a common denominator here. You can know that this, of course, is 3/2, or you can do the shortcut, 2 plus 9 over 6, which is 11 over 6. Okay, so once again, all I did was take the antiderivative just like I used to. Individually, these are x to the nth. So I'll increase the power by 1, divide by the new power, and I'm going to put in the top number first minus the bottom number into that antiderivative, and there is no longer a plus c. Another example, the definite integral from, let's do 1 to 4 of root x plus 1 all over x dx. Well, obviously, you know, if you choose a u here, you're not going to get back a good du. So once again, look to use algebra to simplify things first. So I can divide each of the tops over the bottom, and this would become, this is x to the 1/2. So x to the 1/2 minus 1 would be x to the negative 1/2. And this would be plus x to the negative first. Do not bring anything up. I'm not bringing anything up. All I'm doing is dividing here each of these by x, subtracting the exponents, top minus the bottom. So 1/2 minus 1 gives me to the negative 1/2 power, and 1 over x gives me x to the negative first. And we can bring down the, you know, from 1 to 4, the limits of integration, dx. So just ignore the limits of integration and just focus on taking the antiderivative just like we used to. So we're going to increase the power by 1 on each of these, and we'll get x to the 1/2 multiplied by its reciprocal, which is 2 root x, or 2x to the 1/2. And remember, this is 1 over x. Or if you were to increase this by 1, you would get x to the 0, and you can't divide by that. So that should tell you that the antiderivative is the ln of the absolute value of x. Remember, you cannot divide by 0, so 1 over x, its antiderivative is the ln of the absolute value of x, from 1 to 4. Now we can restore back our limits. So once we've taken the antiderivative, we're just going to evaluate this antiderivative at these limits. So it's really not much anything new. You're just going to take the antiderivative just like we used to, and you're going to evaluate that antiderivative at these limits of integration, we call them. But the top number goes in first minus the bottom number. So I'll put the 4 in first and get 2 times the square root of 4 plus the ln of 4, and the absolute value of 4 is 4, minus, this is the important part, minus, 1 goes into here, the square root of 1 is 1, times 2 is 2, plus the ln of 1. So this is 2 times 2, which is 4, plus the ln of 4, minus 2 minus the ln of 1. You have to distribute that minus through there. The ln of 1 is 0, so that's gone. And 4 minus 2 is 2, plus the ln of 4. Okay, so there's our answer then. 2 plus the ln of 4, and that cannot be simplified. All right, now we'll focus on those that require u substitution. So once again, really not anything new. Just taking the antiderivative and evaluating that antiderivative at the limits of integration, the top number minus the bottom number. Another example, number 3. The definite integral from 0 to 1 of x squared plus 1 to the third power times x dx. Well, obviously when we see a power here, we're going to look to do u substitution. So we're going to do u equals the inside stuff, x squared plus 1, and du equals 2x dx. I'll put a 2 in, take out a 1/2. Again, ignore the limits of integration for right now. This will become 1/2 times the indefinite integral of, well, this, you know, becomes my du, and this will become u to the third. Okay, now, we're going to take this antiderivative in terms of u. So therefore, we need now our limits of integration to be in terms of u. So remember, these are in terms of x's. How can I find out what they are in terms of u? Well, when x is 0 right here, I'll just put 0 in for x right here and get that u is 1. When x is 1, I'll put 1 into here. 1 squared plus 1, you know, is 2. And just ignore those limits of integration. You know, if you want, you can leave them out even for the time being, and then restore them at the end. The antiderivative of u cubed is u to the 4th over 4 times the 1/2, but we have to bring back them eventually. So now I'll put bracket, one bracket at the end to designate that I'm going to evaluate this from 1 to 2. You can bring out the constant. You know that 1/2 times 1/4 is 1/8. So it'd be 1/8 times u to the 4th from 1 to 2. And then now I have to put my limits of integration in. So it'd be 1/8. Top goes in first. So it'd be 2 to the 4th minus 1 to the 4th. And we know that 1 to the 4th is 1, and 2 to the 4th is 16. Minus 1 is 15 over 8. And once again, you can always check yourself by putting this into the TI-83 and the Math 9 and verify that your answer is correct. Okay, so I could have kept the limits of integration even back here if I'd wanted to, from 1 to 2 of u cubed du. But just focus on taking the antiderivative just like we used to. And take that antiderivative and then evaluate that answer at your limits of integration, the top minus the bottom. Okay, let's do another example. Another one. The definite integral from 1 to 6 of the square root of x plus 3 dx. So u will be equal to x plus 3, du will be equal to 1 dx, and this becomes the indefinite integral of root u du. So again, just ignore the limits of integration for right now. That antiderivative is, well, that's u to the nth, that's u to the 1/2, increase the power by 1, so that's u to the 3/2, multiply by its reciprocal. Now you've got to evaluate that at your limits of integration. So when x is 1, u is 4, and when x is 6, u is 9. And I can bring out the constant 2/3, like that. And I'm going to evaluate this from 4 to 9. So the top number goes in first, the upper limit goes in first, so it's 9 to the 3/2 minus 4 to the 3/2. The square root of 9 is 3, cubed is 27, and the square root of 4 is 2, cubed is 8. And then now we'll subtract and multiply, and we get here 19 times 2/3, or we can double that there and get 38/3. Double the top and get 38/3. Okay? Next, another example using a trig function. The definite integral from 0 to pi over 2 of cosine cubed x times sine x dx. Choose u to be the inside stuff, cosine x du. Here's where a lot of you are making mistakes in taking your antiderivatives. Once you choose u to be cosine, the derivative of a c function is a negative answer. A lot of mistakes on your previous test were coming up that you were not putting in the negative. Put a negative in, take one out, so all of this will become the du, and this will become u cubed. So this becomes the negative indefinite integral of u cubed du. And just that's u to the nth, so its antiderivative is negative u to the 4th over 4. But now we have to evaluate that antiderivative. So this is for when, again, x is 0. So I put 0 in for x right here. The cosine of 0 radians is 1. I put pi over 2 in for x. The cosine of pi over 2 is 0. Now notice I'm integrating here from a higher number to a lower number. And I have a negative in front. So we learned yesterday that when we reverse the limits of integration, or flip them, we flip the sign from negative to positive. So this would be u to the 4th over 4 from 0 to 1. If you change the limits of integration, you change the sign on the integral. So then now this becomes 1/4 minus 0, or just 1/4. Okay. Next. Just some other kinds of functions. But the idea is the same, just as before. Take the antiderivative and evaluate it. The definite integral from 1 to 3 of e to the 4x minus 3 dx. So it's the exponential function e, so let's choose u to be 4x minus 3, and du is 4 dx. Put a 4 in, take out a 1/4. So this becomes 1/4 times the indefinite integral of e to the u du. And that answer, e to the u du, is e to the u. But again, no plus c now. So now we're going to evaluate that antiderivative at our limits of integration. Again, when x is 1, 1 into here we get is 1 is for u. And we put 3 into here, we get 9. So I can bring out my constant and put in the top first, the top limit first, e to the 9th minus e. So this becomes e to the 9th minus e to the 1st. And obviously we can't do anything else with that, so we can leave it as that. Okay. Another one, or two, is the definite integral from 0 to 3 of x dx over x squared plus 9. So we would know that a good choice for u would be to choose the denominator, x squared plus 9. Du equals 2x dx. Put a 2 in, take out a 1/2. So this would become 1/2 times the indefinite integral of du all over u. And we know that that answer is 1/2 times the ln of the absolute value of u. But again, that's where we'd put the plus c. There's no longer a c. We're going to evaluate that at our limits of integration. So when x is 0, u is 9. And when x is 3, 9 plus 9 is 18. So the top limit goes first, and the bottom limit goes second. So this would be, well, I didn't show the work here. This would be the difference in the ln's is the ln of 18 divided by 9. I can make one ln. From 2 ln's to 1, So the ln of 18 minus the ln of 9 is the ln of 18 over 9, which is the ln of 2. I can also, if I wanted to, take this back up on top and make it the ln of root 2 if I wanted to. Okay. Next, one more example. The definite integral from 0 to 1 of tangent inverse of x quantity cubed over 1 plus x squared dx. Okay, so obviously a good choice for the u would be the inside stuff. So choose u to be tangent inverse of x. Its derivative is 1 over 1 plus x squared dx. 1 over 1 plus the inside stuff squared times the derivative of the inside. And we've got this exactly. So this would become then, this is my u, so this would become u cubed du. It's u to the nth, so its antiderivative would be u to the 4th over 4 plus, no plus c now. That's the old. So then now our limits of integration will become what? So now when x is 0, what's the tangent inverse of 0? When we see the inverse notation, we should know that that means to find me what angle where tangent is 0 radians. So the coordinates at 0 radians right here, where they're 1, 0, tangent is y over x, y is 0, x is 1, so that becomes 0. Now, when x is 1, what angle has a value of 1? That is a tangent value of 1. So tangent inverse of 1 means to find the angle where the tangent value is 1. Tangent's positive here, and of course we know here, but nothing's in that quadrant for the inverse function. 1, 1, root 2. Our reference angle is pi over 4, so we should know that that is pi over 4. So then we put in pi, you can factor out the 1/4 and put in the pi over 4 to the 4th power minus 0. So that would then end up being pi to the 4th over 4 to the 4th times this 1/4 yet back here minus 0. And that would just leave us pi to the 4th over 4 to the 5th. And we don't have to simplify that anymore. I think that's good enough. So again, this is a great way to find the value of the definite integral. Sometimes we will still have to use geometry because we won't end up with something that we know the antiderivative of. That something, for example, is the definite integral from 0 to 5 of the square root of 25 minus x squared dx. If I choose my u to be the inside stuff, I would get du equals negative 2x dx. I cannot put a variable in there. So u substitution would not work. Well, what will work is geometry still. Graphing this as a semicircle from negative 5 to 5 of radius 5 and using my area formulas. Okay, so we still have to rely upon the other methods we've learned to often evaluate the definite integral. So this lesson, the bottom line is you take the antiderivative just like we used to. If your antiderivative is in terms of x's, where it's just x to the nth, then you increase those powers by 1, divide by the new power, and there's no need to change the limits of integration. You're only changing the limits of integration when you do u substitution. So you evaluate the integral just like you used to, taking the antiderivative, not putting a plus c, and evaluating that indefinite integral at the limits of integration, as we call it. You know, why is it not necessary to put a plus c? We could technically put a plus c, but what happens is in the evaluation process, the constant would only cancel out. So for example, if I put, just say for example, plus 1 here, and it's plus any constant, because we know the derivative of a constant is just going to be 0. So if I attach this, u to the 4th plus over 4 plus 1, when I put my limits of integration in from, what were they there, 0 to pi over 4, when you go to put these in and subtract, the constant's only going to drop out. So that's why it's not necessary to put in a constant in your antiderivative, because through the evaluation process, the constant's only going to subtract out when we go the upper limit into the into this minus the lower limit into that. Okay, so again, just to summarize it and clean it all up, you take the antiderivative. If it's like the x to the nth and you did not do u substitution of any nature, then you leave it in terms of x's. Your limits of integration stay in terms of x's. Like for example, with this one, the definite integral from 1 to 2 of 1 over x dx. Well, we know that's 1 over u du. Its antiderivative is the ln of the absolute value of x from 1 to 2. Well, I'm not going to change these. I have no u substitution, so the limits of integration will stay the same. So it's the ln of 2 minus the ln of 1, and this we know is 0, which is the ln of 2. Here's a good example. If I had included a constant, call it plus c. What happens is in the evaluation process, when I put my 2 in, and I distribute the negative, the c's only drop out. So that's why it's not necessary to put a constant in for your antiderivative. And if you do u substitution, then you have to change these limits of integration from x's to u's and keep that answer in terms of u's, at the end. When you do, like again, something like x cubed over x to the 4th plus 1 dx, if you choose u to be x to the 4th plus 1, du equals 4x cubed dx, put a 4 in, take it a 1/4. I'd have 1/4 the, let's see, du over u, and if x is 0 here and it's 1 up here, then this would become 1/4 the ln of the absolute value of u from what? Well, when x is 0, I would get 1 down here for u, and when x is 1 up here, I would get 2 for that. Okay, so keep this then in terms of u, and then keep these in terms of u, and it helps things to simplify a lot easier. Okay, so there's our lesson. Evaluating the definite integral by using the antiderivative in our limits of integration.